Hello, this is lecture, and in this lecture I will explain queuing theory. First part of the queuing theory, Poisson process or interarrival time distribution, we have already done. Now I start. A problem of queuing arises when a flow of customers from finite or infinite population towards service facility form a queue on account of lack of capability to serve them all at a time. The queue may be of persons at a doctor's clinic or at a railway booking office. These may be machines waiting to be repaired at a workshop, or of ships in the harbor to be unloaded, or of letters arriving at a typist's desk, etc. In queuing, the term customer we mean arriving unit that requires some service to be performed. Now, queuing system, the general framework of a queuing system has been given in this diagram. This is arrival of customer. After arriving, they join the queue, and this is showing waiting of customers, and then queue discipline. Queue discipline, I will explain it after some time. Then service mechanism and served customers leaving from the system. So therefore, the first thing, arrival of customers, they join the queue, they are attended by servers, and after getting their service, they depart from the system. This is there. Now, customer behavior. There are three types of customer behavior. First, barking, reneging, joking. Barking, if a customer decides not to join the queue because the queue is too long, and then he leaves the system, then it is said to have barked, or the customer is said to have barked. Second customer behavior is reneging. If a customer joins the queue, but after joining the queue, he loses his patience and then he leaves the system, then he is said to have reneged, or this process is called reneging. Joking. If a customer joins one queue and then move from one queue to the another, this is called for his personal gain, economic gain, or some other types of gain, then the customer is said to have jockeyed for position. Queue discipline. Queue discipline, it is a rule according to which customers are selected for service when a queue has been made. It may be first come, first served, or we say this first in, first out, or last in, first out, or service in random, or this service in random order, CSIRO, or preemptive priority. So therefore, in queue discipline, it is the rule by which the customers are to be serviced. And there are three kinds of rule. First is first come, first served, or first in, first out, or last in, first out, or service in random order, or preemptive priority. Sometimes it is there, then in this queue discipline, some customers are to be given priority. But usually we consider this first in first out or first come first served process. So customers behavior I have explained. There are three kinds of customers behavior barking. When a customer does not join the queue, then he is said to have barked. Reneging, if a customer enters the queue but after some time he loses his patience, then he leaves the system, then it is said to have reneging. Jockey, if a customer moves from one queue to the another queue. Now it is their service mechanism. Service mechanism is concerned with service time and service facility. So therefore, in service mechanism there are two things. Number one, service time. Number two, service facility. Service time, it is the time interval from the commencement of the service to the completion of the service, or we can say it is the duration of service. Service facility, there may be a single server, single queue, one server, or we can have single queue, several servers. Suppose there is only one queue in the system, but there are two or three servers. Third type, several queues and one server. There are say 2-3 queues. They may be parallel queues, parallel waiting lines, but server is only one, or several servers. So therefore in service facility parts, it is there that what kind of service facilities do we have. It is there only one server or two server or three server, or it is there only one waiting line or two waiting line, or one waiting line more than one server, or several server, several servers but waiting line is only one. So this is about service facility. Again, service mechanism in queuing system has two components, one service time and the other service facility. Service time is the only time duration of the customer is spent in service, and service facility means what kinds of server or what kinds of waiting lines do we have in the system. There may be one server, two server, three server, there may be one waiting line or queue, two waiting line or queue, three waiting line or queue, or one waiting line, one server, two waiting line, one server, three waiting line, one server, or only one waiting line or two server, three server, etc. Now, general queuing model is described by Tyndall notations. This model, queuing model, general model is specified in the following symbolic form: A/B, B/C, then D/E. Here, the first and second symbols denote the types of distribution of arrival and interval time distribution between two arrivals. So therefore, A is the notation for the arrival distribution, which is usually their Poisson distribution, or it follows Poisson process. The second one is inter-arrival time distribution, which is their exponential distribution, because we have already seen if arrivals follow Poisson distribution, then the inter-arrival time between two successive arrivals always has exponential distribution. So B, for this inter-arrival time distribution, A for arrival distribution. Arrival distribution, that is Poisson process or Poisson distribution. B, exponential distribution, inter-arrival distribution. Sometimes we do have also Erlangen distribution. We do use Erlangen distribution, which is Erlangen variate is the sum of exponential variates. Then the fourth symbol is denoting the capacity of the system. We have finite capacity or infinite capacity. And the last one, E, is the last symbol denotes Q discipline. Q discipline, as we have already seen, in the Q discipline we do have whether it is first come first served process or last comes first served process or service in random order, or this preemptive priority. We are going to give some of the customers as priority. Now, if say for example in this M, E, K, I infinity first in first out, here M Poisson process, arrival is having Poisson process, but the second is not exponential, but it is the Erlangen distribution, which is generalization of the exponential distribution, or exponential variate is the sum of Erlangen variate is the sum of exponential variates. And infinite capacity, first in first out. So now definition of this transient and steady state. Transient state, a Queen system is said to be in transient state when its operating characteristics like input, output, mean Q length, etc. are dependent upon time. This is called transient state. So in transient states, the operating characteristics, input, output, mean Q length, etc. are dependent upon time. But in steady state, if the definition of a steady state is if characteristics of Queen system becomes independent of time, then this state is called steady state. So again here, if characteristics of the Queen system becomes independent of time, then we say that it is their steady state. So now, if P and T, this is the symbol P and T, denotes the probability that there are n customers or units in the system at time t. So then in steady state case, we have a limit t tending to infinity, P and T is equal to Pn. In most of the cases in the start, the system behaves like transient state, but after a gap of time, it assumes the steady state. So we are having here limit t tending to infinity, P and T is equal to Pn. Pn, we have no function of P now, Pn is not depending on time. So this is the symbol for steady state case. And if it is P and T, the number of customers are the units in the system at time t. So here it is depending on time. So P and T is the transient state symbol we can say, and it is converted to Pn only if it becomes in steady state. Now I will explain the Queen model first. The Queen model first is denoted by M/M/1 or first infinite oblique FIFO. Now this M means arrivals have Poisson process or Poisson distribution, because Poisson process is a Markov chain. So that is why the arrival distribution is designated by here N. And then the second symbol is for inter-arrival time distribution. So then if it is Poisson arrival, then second one, this second N is denoting here the inter-arrival time distribution. So if we do have Poisson arrival, then inter-arrival distribution is exponential. So therefore both first symbol and second symbol A, B we can say are designated by M. The third symbol, only one service station. Third symbol, one service station. The fourth symbol, infinity, infinite capacity. And then first in, first out, or first come, first served process. So now here in this system, lambda is taken as mean arrival rate, and as I have explained in Poisson process, the probability of one arrival in delta t time is equal to lambda delta t, and this delta t is so small that during this time more than one customer we cannot have, more than one departure we cannot have, more than one service we cannot have. So probability of one arrival in delta t time is lambda delta t, and therefore the probability of no arrival in delta t is 1 minus lambda delta t. Why? Because there are only two cases. Either in delta t time we can have one customer, or we can have no customer. So therefore if the probability of one customer is lambda delta t, the probability of alternative is that is having no arrival in delta t time is 1 minus lambda delta t. And now if mu be the mean service rate, mu is the mean service rate, then the probability of one service in delta t is mu delta t, because the departure distribution has Poisson distribution, but with mean as mu t, not lambda t. So probability of one service in delta t is equal to mu delta t, and probability of no service similarly, because in delta t is so small that during delta t time we cannot have more than one service. The possibility is there that during delta t time either it is one service or no service, and if the probability of one service is mu delta t, the second alternative event is no service. The probability of that event, complementary event, 1 minus mu delta t. Now I am going to define the event of n units in the system at the elapse of time t plus delta t. first case n greater than 0. So, which event I am going to define here? I am defining the event of n customers in the system at the time or at the elapsed of time t plus delta t. And it is clear that in delta t time only one customer can be adjusted or no customer. Similarly, in delta t time only one service can be adjusted or no service. So the event of having n units at the time t plus delta t can happen in any one of the four mutually exclusive ways. The first way, n units in time t and no units, no arrival in delta t, no service in delta t. So after the elapsed of time t plus delta t, we will have the n number of units at time t plus delta t, because all the n units in time t, so therefore in delta t we cannot have any arrival, we cannot have any service. If we will have say one service in delta t, it will become n minus 1. So it is the first case, the event of having n customers at the time or after the elapsed of time t plus delta t is n. So this is the first event, the event of having n customers at the time of t plus delta t can happen either in this way, that n units in time t, no arrival in delta t, no service in delta t. The second way is n arrivals in time t, but one arrivals in delta t and one service in delta t. So we are having n arrivals in time t. In delta t we are having one arrival, but one arrival at the same time is being serviced during delta t. So therefore in this the number of arrivals is n after the elapsed of time t plus delta t. We have the result of t time, we have the result of delta t. So this is the second mutually exclusive way. And the third mutually exclusive way is this: if n plus 1 arrival in t, n plus 1 arrival in t, no arrival in delta t, but one service in delta t. Because the answer should be here, after the elapsed of time we should have only n units, but in time t we are having n plus 1. So it means one is to be serviced in delta t and no arrival in delta t. If we will have here one arrival in delta t, then it will remain same as n plus 1, because one service is in delta t. Now the fourth case is n minus 1 arrivals in time t. So we should have one more arrival to make it n during delta t, one arrival in delta t and no service in delta t. If you will have service, here n minus 1, 1 is here, and then one service, it will become again n minus 1. So the question is this: why I am taking only the case of n plus 1 arrival in time t or n minus 1 arrival in time t, not n plus 2, not n minus 2? It is because after t it is delta t time and during delta t time we can have either one arrival or one service or both. But if we have here n plus 1, so then no arrival in delta t and one service in delta t. If we have here n plus 2, two arrival or two service to make the total n units after the elapsed of time t plus delta t. If I have here n plus 2, then two service cannot be done during delta t to make n plus 2 minus 2 as n. And similarly here, n minus 1 unit in time t, and not n minus 2, n minus 1 in time t, no problem. One arrival we can have during delta t and no service in delta t to make the result total number of customers after the elapse of time as n. So therefore, these are the only 4 mutually exclusive ways, and the event of having n customers at the elapse of time t plus delta t can happen in any one of the 4 mutually exclusive ways. It is not there that this will happen, this will happen, this will happen, this will happen. No, not at all. If this happen, it cannot happen, it cannot happen, it cannot happen. These 4 events are now mutually exclusive. But within one event, you see, n units in time t, no arrival in delta t, no service in delta t. The event not complete, n units having after elapse of time. If we don't have this, we don't have this. After t time, we have to show the result of delta t, whether during delta t it is one arrival or it is one service. So therefore, this should happen, this should happen, this should happen. So if it is the situation, A should happen, B should happen, C should happen, so it is the probability of A into probability of B into probability of C, or it is simultaneous occurrence of the events. So here, this to this, it is simultaneous occurrence of 3 events, this. So within this, the probability of this event, whole event, will be equal to product of this probability, and this probability. Similarly, for second case, we have 3 sub-events. We can say this should happen, this should happen, this should happen. So here, within this event, we will have multiplication. Probability of this event into probability of this event into probability of this event. Similarly for third and fourth case. And as you know, if we have 4 mutually disjoint events, then the probability of their union is equal to sum of their separate probabilities. Probability of A union B union C union D. If A, B, C, D are mutually disjoint or mutually exclusive, then it must be equal to probability of A plus probability of B, probability of C, probability of D. So therefore, the required probability. Now I am attaching with the events, I have defined events only. Now I am attaching the probability. Probability on left hand side is denoted by this symbol P and T plus delta T. Probability of having n units at the elapsed of time T plus delta T. But this event can happen in any one of the following, any one of these mutually exclusive events. So the probability of this event is equal to probability of this plus probability of this plus probability of this plus probability of this. Now A, first probability of n units in time t, then occurrence of this, then occurrence of this. Within this, it is product or multiplication of these 3 probabilities. So in the first part, you see probability of n units in the time t, P and T, no arrival in delta t, no arrival in delta t probability is 1 minus lambda delta t. See this. And then no service in delta t, no service probability 1 minus mu delta t. So P and T 1 minus lambda delta t, 1 minus mu delta t, plus second, this one, probability of n arrivals in time t, p and t. No one arrival in delta t, one arrival in delta t, lambda lambda delta t, and no service this mu delta t. This is the second one, this one. Now third one, first is probability of n plus 1 units in time t. Probability of n plus 1 units in time t, and then it is no arrival in delta t, 1 minus lambda delta t, and then one service in delta t, mu delta t, this. And now the fourth one, n minus 1 arrival probability in time t, Pn minus 1t, and then one arrival in delta t, one arrival in delta t, lambda delta t, and then no service in delta t, 1 minus mu delta t. So therefore in these four probabilities we have used within an event the multiplication theorem on probability, and also we have used, if the events are disjoint, then the probability union is equal to sum of their separate probabilities. This first plus second plus third plus fourth. But within this, it is multiplication, simultaneous occurrence of three events. This probability of n in t, no arrival in delta t, no service in delta t. So these are the four cases, and their required probability, sum of four probabilities is equal to p and t plus delta t, where n greater than 0. Now simplifying this p and t plus delta t, I can write here p and t plus delta t. This is equal to simplifying this, we have p and t plus delta t minus p and t minus lambda plus mu delta t p and t mu delta t p n plus 1t, and this p and t plus delta t minus p and t, dividing this throughout by delta t, or delta t in the right hand side we see it is common, so bringing this in the denominator, we have here p and t plus delta t minus p and t over delta t is equal to minus lambda plus mu p and t plus mu p n plus 1t plus lambda p n minus 1t, and delta t is very small, so letting delta t tending to 0. So what do we have on the left hand side? When delta t tends to 0, it is the derivative of p and t. Derivative of p and t, that is p dash n t is equal to minus lambda plus mu p and t plus mu p n plus 1t plus lambda p n minus 1t. So this is the differential equation. It has suffixes, it has derivative. So it is not only differential equation, not only this difference equation. So it is differential equation for the model MM1 infinite Fi Fo, and when n greater than 0. So in my another lecture, I will discuss the second case when n is equal to 0 or there is no arrival in the system at the elapsed of time t plus delta t. We will derive its differential equation, and then we'll solve the two differential equation. Thank you.